Endothermic and exothermic reactions. So the goal of this video is to, first of all, distinguish between exothermic and endothermic reactions, to identify the energy changes involved in breaking and making chemical bonds, and lastly, to define activation energy. From what we've looked at so far, we are aware that combustion reactions are useful in many aspects of our lives because of the heat that is produced. Now, the question to consider here is, do all chemical reactions produce heat? Keeping that question in the back of your mind, let's start looking through today's notes. So, what you can see on this screen is that there are two images. On the left-hand side here, we can see that when concrete sets, it releases energy, therefore heating it up. As a result, for large structures, engineers must ensure that the concrete cools evenly so it doesn't crack. On the right-hand side here, compost heaps grow hot because of the chemical reactions that take place as microbes break down organic matter. One thing to note is that when microbes actually break down organic matter, that's when our foods begin to rot. The process of rotting itself is a chemical reaction, and as a result, it releases heat because it does grow hot. So, reactions that release energy are what we call exothermic. The energy is usually released as hot, where exo means out, and the word thermo means heat. However, sometimes it is also released as light or even sound. Now, down below here, there is a quick video that shows how heat is viewed in a heat-sensitive camera. So I won't play this video in this recording, but if you pause it and actually go into your activities and play it, you can actually see that when an exothermic reaction takes place and a heat-sensitive camera is pointed towards it, you can see the heat being released, and as a result, this camera picking up that heat signature. So, relating to all that we've just talked about, there are a few questions to answer. Question number 1. The reaction between magnesium and hydrochloric acid is classified as exothermic because it A. involves a solid reactant, B. releases heat, C. takes place very quickly, or D. produces gas. From the information that we're given just above here, it tells us that if it is an exothermic reaction, it means it is a reaction that releases heat. Based off the options that were supplied here, the only one that meets that criteria is option B. So if we go ahead and just check that, that will confirm it. Question 2. In your own words, describe what happens in the second reaction of the video. Remember, be observant, report everything you see that seems relevant. Now, if you've paused this video and had a chance to look at this clip here, the second reaction that they are talking about, what you would have seen is that water at room temperature is placed in a beaker. A small amount of a clear liquid is added, and the mixture starts bubbling immediately. It almost looks as though it is boiling. Viewed through the heat-sensitive camera, you can see that the reaction mixture is hot, white-yellow in appearance, and that some of it spatters against the sides of the beaker because of the bubbling. A hot gas rising from the mixture shows up as orange and seems to pulsate. The lower part of the beaker, containing the liquid, heats up quickly to yellow-orange on the camera's temperature scale. It seems to be hottest at the top of the liquid, but then the upper half of the beaker is significantly cooler, as implicated by the purple-blue color. The heat also spreads out in the surrounding air and bench. Now, down below here we have two images. On the left, we can see a firefighter using a fire extinguisher which works partly by absorbing the heat released from these flames via the chemical breakdown of sodium bicarbonate, which is contained in the fire extinguisher here. So by releasing that sodium bicarbonate, it actually starts to absorb the heat from the fire, and eventually it will die out. On the right hand side here, we can see someone applying a cold pack. The cold pack itself is made up of a chemical reaction that is designed to absorb heat. We are more used to the idea of chemical reactions that produce flames, explosions, and other forms of energy. But not all reactions are exothermic. Reactions that absorb energy are called endothermic, where the word endo means in or inside. So an endothermic reaction takes in heat, so it absorbs heat from its surrounding to the body. There are some instant cold packs that use this type of reaction to treat injuries. For example, this cold pack that we discussed just then. Once again, there is a short video for you to watch, so if you pause this recording, you can take a moment and look through that. Question 3. Exothermic reactions are A. Absorbs energy causing an increase in temperature. B. Absorbs energy causing a decrease in temperature. C. Release energy causing an increase in temperature. Or D. Release energy causing a decrease in temperature. With the information that we are given up the top here, we are aware that endothermic reactions absorb energy from the environment in order to cool down. As a result, the only plausible option here is B. Endothermic reactions absorb energy, therefore causing a decrease in the temperature. With question 4, a chemical reaction occurs when you place sherbet on your tongue. Which of the following is a sign that the reaction is endothermic? A. A sweet taste. B. The sensation of coolness. C. The fizzing sensation as bubbles of gas are produced. Or D. The sharp, tangy flavor. So what you should be aware of now is that endothermics are reactions that get colder by absorbing the energy from the environment. As a result, the only plausible answer is B. The sensation of coolness tells us that an endothermic reaction is taking place. Moving on to question 5. You have been asked to sum up the difference between exothermic and endothermic reactions by dragging the missing terms into place. So this first sentence here. Something reactions absorb energy, so the temperature of the surroundings something. What we're looking for here is a type of reaction that absorbs energy. So, the reaction that absorbs energy is an endothermic reaction. So if we go ahead and just move that over into place. So an endothermic reaction absorbs energy, so the temperature of the surroundings decrease because that energy is being pulled from the environment or the surroundings to wherever it is taking place, so to the reaction itself. So, the second sentence. Something reactions release energy, so the temperature of the surroundings something. So, what we're looking for here is an exothermic reaction releases energy, so the temperature of the surroundings increase. Now, an easy way to remember an exothermic reaction is an explosion. An explosion releases heat into the surrounding, so the surroundings get significantly hotter. Moving on to breaking and making bonds. Now that we are able to recognize exothermic and endothermic reactions, let's take a look at them up close. To explain why some reactions release energy whereas others absorb it, we need to understand what's going on at an atomic level, so looking at the atoms themselves. So, all reactions involve the rearrangement of atoms to form a new substance. This involves two steps. The first step is to break the bonds in the reactant molecules. This requires energy from the surroundings. Step 2, making bonds. So this is where bonds are made to form new product molecules. As a result, this releases energy back into the surroundings. The two steps, the first requiring energy and the second releasing energy, this all takes place in all reactions, both exothermic and endothermic. The difference here is whether the amount of energy released when the new bonds form is greater or less than the energy required to break the bonds. So if we look at this diagram on the right here, what we can see is that there is a reaction between hydrogen and oxygen. So it tells us that with our reactants, so your starting materials, your reactants are up the top. When their bonds break, we lose these connecting components. So all of these are now separated. All of these atoms are now separated. Then we need to rearrange these molecules or these atoms, and we need to create new bonds to form new products. As a result, we need energy to break these bonds. Then we need energy to remake new bonds in different sequences or different arrangements. So this itself is a chemical reaction shown. Now, the activation energy. The energy required to break bonds is what we call the activation energy. It is always required to start a reaction. For example, gas ovens and grills need a match or a spark to start them, so as shown on the side here. Similarly, a spark is needed to ignite the fuel and air mixture in a car engine to get it started. So, the activation energy differs for different reactions. Some reactions need a lot of energy to start it off, others not so much. With question 6, breaking chemical bonds, A, require energy, B, release energy, or C, does not involve an energy change. So, with what we learnt between these two paragraphs here, what we know now is that the process of breaking chemical bonds, so if we look over here, just this line here, breaking chemical bonds in the reactant molecules requires energy from the surroundings. And the only option that supports that is this top one here. So breaking chemical bonds require energy. Now, question 7. Making chemical bonds, on the other hand, actually releases energy. For question 8 here, it talks about activation energy. So, activation energy is A, released when new bonds form, B, always less than the amount of energy released by the formation of new bonds, C, needed to break the bonds in the reactant molecules, or D, required for both exothermic and endothermic reactions. Now, you need to remember that with some of these questions, there are multiple correct answers. If that's the case, select all that apply. With what we've learnt here about activation energy, we are now aware that activation energy is needed to break these bonds in the reactant molecules, but it is also required for both exothermic and endothermic reactions. For question 9, all chemical reactions absorb energy and release energy. Is that true or false? hopefully you would have figured out that it is true. The reason that it is true is because even endothermic reactions release energy, but less than what they absorb. So your endothermic reactions absorb energy from the environment, but they still release a very small amount. Moving on to question 10. Which reaction has the higher activation energy? Is it between hydrogen and oxygen, or between hydrogen and nitrogen? What we're looking for here is that the correct answer would be hydrogen and nitrogen. So the reason for this is because you have to put in more energy for this reaction to actually take place. 7 in comparison to 4 for hydrogen and oxygen. For question 11, which reaction has the lower activation energy? Methane and iodine, or hydrogen and iodine? The correct answer here would be between hydrogen and iodine, and the reason for that would be because this particular reaction requires 1 input of energy in the simulation compared to 3 for methane and iodine. If we move on to question number 12, which reaction releases the greater amount of energy from forming new bonds? Would it be methane and oxygen producing carbon dioxide and water? Or would it be between methane and oxygen producing carbon monoxide and water? What we would be looking for here is that the reaction between methane and oxygen would release more energy because the formation of carbon dioxide and water releases the most energy. For question 13, if the amount of energy released by a reaction is greater than the activation energy needed to start, then the reaction must be A, exothermic because overall energy is absorbed, B, exothermic because overall energy is released, C, endothermic because overall energy is absorbed, or D, endothermic because overall energy is released. Well, to start off with, let us rule out the ones that we know are incorrect. Let's look at option A. It says it's exothermic, but it's then talking about energy being absorbed. From what we know, exothermic reactions actually release heat, so it cannot be an absorption of energy. So we can rule out answer A. If we then look at answer D, endothermic because overall energy is released. Well, if you think about it, endothermic reactions actually absorb energy, not release energy. So we can actually rule out answer D. That leaves us between options B and C. Now, if we reread the question, if the amount of energy released by a reaction is greater than the activation energy required, then the overall reaction must be exothermic because it is releasing more energy than it is required to have to begin. So that overall release of energy is an exothermic reaction. Now, let's look at the chemical energy itself. We can explain the energy changes in these reactions in terms of the energy stored in the chemicals. Different chemicals have different amounts of energy in them due to the way their atoms are bound together. This is their chemical energy. In exothermic reactions, the products have less chemical energy than the reactants. So the extra energy is released to the surroundings. In endothermic reactions, the products have more chemical energy than the reactants. so the extra energy is absorbed from the surroundings. We can actually see these 2 points discussed in this diagram here. So, if we actually just take a look at it, this first point here, in exothermic reactions, the products have less chemical energy than the reactants. Okay, so here we know that this diagram is an exothermic reaction. We've got our chemical energy on the side. So, we've got our reactants, so what we start off with, shown over here. So we know that they're reactants because this all takes place before our bonds are broken. And we also know that down over here, from this line onwards, we have our products. We know they are our products because these bonds have broken and they have rearranged themselves and made new bonds to form our products. So your reactants, what you start with, your products, what you end with. What this is saying in this little sentence here is that in exothermic reactions, the products, so this right-hand side here, have less energy, so it's lower on this chemical energy scale, than the reactants, which is significantly higher. So the extra energy is released to the surroundings. And if we take a look at this bottom diagram here and we match it up with this description here, we know it's an endothermic reaction. So what it reads here, in endothermic reactions, the products, so what you end up with over on this side here, have more, it's higher up on this chemical energy scale. It's got more chemical energy than your reactants, which is down here to begin with. So looking at this height difference, we can see your products have more chemical energy than your reactants. These changes in chemical energy can be represented in what we call our energy level diagrams, which is exactly these types of diagrams here. It's easy to see that the hydrogen and oxygen reaction, so the one with hydrogens and oxygens, so your exothermic reaction over here, is exothermic because more energy is released than it is absorbed. It's also easy to see that our reaction between hydrogen and iodine on this right-hand side below here, reaction is endothermic because less energy is being released than it is being absorbed. A good analogy for this is the landscape of peaks and valleys. The valleys represent states in which atoms form molecules or lattices. These are stable states with low chemical energy, and atoms naturally go into them, like boulders rolling down into valleys. A chemical reaction is like getting a boulder from one valley to another. You first need to roll the boulder uphill, representing the activation energy needed to break the bonds in the reactants. So shown by this component here. So rolling the boulder uphill is the activation energy, so the energy that's required to start the reaction. And then the boulder rolls down into the next valley, which represents the energy that's being released as the new bonds form. So your activation energy is the energy required to start your reaction, so to get this boulder up to the top. Once your new bonds are being made, it is like the boulder being released into the valley. Then it breaks the bonds again, and then it makes the bonds again. So this diagram here shows that it's an exothermic reaction, and it simply shows us that breaking the bonds is like requiring the activation energy. Once it hits the peak, it drops down again, which is making these new bonds. So if we look at the endothermic reaction, pushing the boulder uphill, up this valley, requires significant amounts of energy. However, to create these new bonds, that boulder only rolls slightly downhill, so only a small amount of energy is released. So, based on the above, for question 14, in both endothermic and exothermic reactions, the amount of chemical energy increases and then decreases. What we are looking for here is that that is actually true. The reason for that is because all chemical reactions require activation energy, which is energy from the surroundings that goes into chemical form as bonds break. So chemical energy always increases first. Then chemical energy lowers as these new bonds are formed. For question 15, in endothermic reactions, do the reactants or products have more chemical energy? For endothermic reactions, let's take a look at this one here. It's asking us if our reactants or our products have more energy. So, chemical energy is shown on this left-hand side scale. So the higher it is, the more energy is released. So, to start off with our reactants, the energy there is actually quite low on this scale. But if we then go to our products, if we trace this all the way across, the energy level on our products is actually quite high. So what you could say for question 15 is that the products have more chemical energy than the reactants, so this energy has to come from the surroundings. For question 16, imagine a reaction in which the chemical energy of the products happen to be exactly equal to the chemical energy of the reactants. This reaction would be exothermic, endothermic, or neither. So, the correct answer here would be neither, and the reason for that is because if the reactants and products both have the same amount of chemical energy, then overall no energy will have gone into or come out of the surroundings. For question 17, in that mountain analogy, what do the peaks represent? From the info that we are given in this paragraph and what we see in this diagram, what we can say is that the answer would be D. The atoms are not bonded together. They're unstable, high energy arrangement. So, at the graph peaks, the chemical bonds of the reactants have broken, but new bonds have not yet formed. So the atoms are not bound and have high chemical energy. For question 18, which have more chemical energy? One N2 molecule and one O2 molecule, or two NO molecules? The correct answer here would be option B, and the reason is because these molecules have more chemical energy than the N2 and O2 molecules that form them. They are produced from an endothermic reaction. For question 19, which have more chemical energy? One CH4 molecule and two O2 molecules, or one CO2 molecule and two H2O molecules? The correct answer would be A, because these molecules have more chemical energy than the CO2 and H2O that is produced if they react. So the excess energy is released into the surroundings. It is an exothermic reaction. Moving on to question number 20. Below is an energy level diagram for the combustion of methane, CH4. Step 1. Drag the molecules and atoms into the larger boxes to show the progression of the reaction. And then step 2. Fill in the labels and complete the sentences with the terms at the bottom. So, with this particular reaction, we are told that our reactants, so our starting materials, is going to be CH4 plus 2 lots of O2. Now, because they are our reactants, they are still bonded together. So, out of the options here, we need one particular diagram that has one particular colored ball and 4 lots of a different colored ball all attached to it. The only available option here we can see is this one here. So by adding this in, what it now tells us is the carbon is shown by this large grey ball, and the hydrogens are represented by these white balls. Keeping in mind that there is 1 carbon, so 1 grey one, and 4 hydrogens, 4 white ones there. Now, with our reactants, we know we've got our methane, CH4, and we also need 2 lots of O2 molecules. Now, given the options that we know here, we know our oxygens are going to be bonded because they still have their bonds, and we need 2 lots of them. So, let's go ahead and pick this option here and this one here. Now what we've got is our CH4 molecule, this one here, and 2 lots of O2 molecules. When we move into this center here, we are now told that the bonds break, which means all of these atoms here, they are no longer joined together. The only option that we can see here is this giant one here. We can actually double check that by counting the amount of atoms we have here. So we started off with 4 white circles, so we've got 4 white circles still here, 1 grey one, 1 grey one, then we've got 4 red ones here, 1, 2, 3, 4. What we're then told is that new bonds are made, where we end up with CO2, keeping in mind that carbon is the grey one, and our oxygen is the reds. So we've got CO2. We've got CO2 here, plus 2 lots of H2O. Keeping in mind the H's are the whites, and the O's are the reds. So here we've got 1 lot of H2O, and here is the second lot. So we've got 2 that we're told here. So what you've just done there is drag the molecules and atoms into these larger boxes. What we now need to do is fill in these particular labels. So, the energy that we are required to start with, what we should remember is that we call that the activation energy. The energy that we end up with is what we call the energy released. So if we go ahead and move those into the right spaces. Down below we have a sentence that we need to answer. The energy released is something than the activation energy from this diagram. As a result, this reaction is something. So, what we can see here is that the energy released is actually lower than the activation energy. So if we bring this line across, the chemical energy sits about here, whereas our activation sits all the way up here. So your energy released is lower or less than the activation energy. So as a result, the energy that's released ultimately is greater than the activation energy. As a result, this is going to be an exothermic reaction. So here we're left with 2 more options, but that is perfectly fine to not use them because everything else is filled out appropriately. So if we go ahead and show the model answer, it will be the exact same thing that we've just done. Then for question 21, we do something very similar to our previous reaction. We will start by placing our molecules and atoms. So we're told that we start off with N2 plus O2. From previous, we know our O2 molecule is going to be a pair of red circles that are bonded, so we'll go ahead and bring that over. And we now need N2, the only possible option here where there are two circles of the same color bonded together is this blue one here. So we've got our N2 plus O2. These bonds are now something, and then the bonds are now something. So during this process up here, what we're going to do is, remember, the bonds first need to break. So if we get rid of these bonds between these two molecules, we will just have this lot of atoms floating around in high energy. So remember, first of all, these bonds actually break. Then the bonds are actually being made. So we're going to go ahead and drag these two options in. So remember, bonds first need to break, which is why we see what we see up here. And then we make new bonds to form two lots of NO. So there's one lot of NO and our second lot over here. Once again, we have a sentence to complete. The energy released is something than the activation energy. As a result, this reaction is something. So, what we can see here is that the energy released is actually less than the activation energy required. So we're going to go ahead and move this one over here. And as a result, this reaction is actually endothermic, just like that. So we'll go ahead and show that model answer, and it's the exact same. Moving on, keeping with our energy diagrams, what we have down below here is 4 possible energy level diagrams. Based off this diagram here, question 22 asks, fill in the table below to say which diagrams, A, B, C, or D fit these descriptions. Now, there are some options that require more than one diagram or more than one answer to it, so let's just be careful. Now, let's pick the diagram that has the greatest activation energy. So what we'd be seeing here is between the point of our reactants and the peak that we can see up here, which one has the highest difference or the largest difference? So for A, we start it here, we can see it up here. So that's about 3 lines worth of energy. For B, we start here, we end here. That's about 2 lines of energy. For C, we start over down here, we end up here, and that is 1, 2, 3, 4 lots of energy. And with D, we start here, we end here, that's 1 lot of energy. So we've got 3 lots of energy, 2, 4, and 1. So the answer here would be C. So we'll go ahead and put a C there. The graph with the greatest release of energy due to bonds forming. What we'd be seeing here is that when your bonds form, if we scroll up here, so when your bonds being made, we're going from the peak to just before your reaction plateaus or your graph actually stays as a straight line. So the difference that we're looking at there is between the highest point, that peak, and just before it starts to flatten off. So this one here has 1, 2, 3, 4, 5 lots of energy. This one starts from the peak, goes down here, that's 1. C, you're starting up here, you go down here, that's 2 lots of energy. And D, we start up here, we end down here, that's 1, 2, 3, 4. So there's 5, 1, 2, and 4. So your answer here would be A. Now, out of your 4 graphs here, which ones are your exothermic reactions? So out of what we can see here, remember, your exothermic reactions, we start with more chemical energy and then it drops. So if we can see that general shape here, so we start higher, then we get lower. This one starts fairly low, gets higher. This one starts low, gets higher. This one starts high and gets lower. So the basic trend of an exothermic graph can be seen from graphs A and D. So we're going to go ahead and go A and D. That leaves us with our endothermic reactions. Now let's take a look at this endothermic reaction. We start lower, it peaks, and it ends up higher. So, starts higher, peaks, ends lower. Starts lower, peaks, ends up higher. Starts lower, peaks, and ends up higher. Starts higher, it peaks, and it ends up lower. So given what we can see in the trends for these 4 graphs, your endothermic reactions would be graphs B and C. And C. So let's go ahead and show our answers, and they should match up, just like we've been talking about. For question 23 here. Now, based off the 4 diagrams that we just saw, which diagram represents the reaction with the greatest overall release of energy into its surrounding? So the overall greatest energy released is seen by D. So the difference between the starting point and the ending point. So the amount of energy starting, the amount of energy ending. There is four levels of energy difference, whereas this one has 2, this one's got 1, and this one also has 2. So what we're going to go ahead is select D. Now, as a final question, let's take a look at this example here. Nitrogen triiodide, Ni3, is a very dangerous explosive. The equation for this reaction is 2Ni3 solid produces N2 gas plus 3I2 gas. The cloud of purple gas produced is iodine, I2, whereas the nitrogen is actually colorless. So if we actually played this video, we could actually see this happen. So it's a fairly short clip, so I will play that for you.
It's always good to start a video off with a bang, and there could hardly be an easier way of doing that than with this stuff.
So what you just saw, if we just scroll that back slightly, the moment that ruler touched that reaction, we heard a bang and we saw that pale cloud of purple gas. I'll play that component again.
Way of doing that than with this stuff.
So the moment that happened, we could see a cloud of purple dust, but also we heard that bang sound. Based off what we just saw there, is this reaction exothermic or endothermic? Hopefully you would have recognized that it is an exothermic reaction. And lastly, how would you describe the activation energy in this reaction? We could actually say the amount of energy required to start this reaction was actually very low. It's extremely low because with the smallest touch, that reaction took place. So just the smallest touch, which is a small amount of kinetic energy, so moving energy, is enough to actually start this reaction. So down here there are 2 very interesting clips for you to take a look at if you're interested, but they just show us very interesting endothermic and exothermic reactions, and you can actually see the amount of heat that is absorbed. So once you've finished going through your answers, going through them, checking that they're correct, making the changes that you need to make, please make sure down the bottom you click on the blue button that says "I'm finished, show my teacher."